Right. Thank you, Duncan, and thanks for the invitation, Duncan and Julian. It's a great pleasure to be able to share some of this work. Duncan, I know you've thought a lot about changemakers and done some great stuff with that. And Steve, we've been in touch a little bit about some of this stuff. So I'm just excited to be able to share some of this stuff now. So everything will be taking place inside of the Poincaré homology sphere. That's now the default 3 manifold. It's not S3 here. But we'll build up to, I want to sketch some of the main proofs, sketch proofs of the main theorems that I want to talk about today. So we'll start out, brief outline, go over some Dehn surgery basics and the main theorems of the day. And then I want to give a brief history of some Dehn surgery results from, I guess, 30, almost 40 years ago now, just to contextualize some of the work that I've done. And then we'll get into this changemaker approach that was sort of discovered by my advisor, Josh Greene, about 12, 13 years ago. And finally, we'll sketch some of the theorems. But I want to start out with a picture. Dehn surgery is the main construction I'll be talking about today. It's the main, cut and paste tool in three-dimensional topology that I care about. So, and I apologize for the resolution on this. I've not seen this on this large a screen before, but the important thing to see here is what we have here is a tubular neighborhood of a knot. This is a solid torus embedded in three-dimensional space. You can see these, these meridional discs sort of hashed out lengthwise along this solid torus. This happens to be a figure 8 knot in S3. And so when you have this solid torus, what you want to do, what you want to think about is scooping out this solid torus. So now you have the exterior of this knot. And then in solid black here, you can see there's an essential simple closed curve on the boundary of the exterior that's been picked out. And so surgery in this picture means taking the exterior of this knot, gluing a 2-handle or a disc to the exterior so that this black curve is now the boundary of this disc. You're left with a 3-manifold that has an S2 boundary. Cap that off with a 3-ball, and that's the result of Dehn surgery on a knot. So it takes in as input an embedding of S1 into a 3-manifold, and then a choice of an essential simple closed curve on the boundary of the exterior of the knot. So in writing, given a knot and a 3-manifold, MK is the exterior. It's the 3-manifold minus an open tubular neighborhood of the knot. And then alpha, we're going to denote by K of alpha, the alpha Dehn surgery on K. That's precisely this manifold we described. If alpha is this simple closed curve that we picked out, we're going to cap that off with a 2-handle and then cap the remaining S2 boundary off with a 3-ball. And when K is null homologous in Y, then it bounds a surface. So by the Seifert longitude, there's actually a canonical identification between the set of slopes, these essential simple closed curves on the boundary of the exterior, modulo isotopy. Everything is just up to isotopy. Isotopic slopes give you homeomorphic surgeries. So we'll mod out by isotopy. But the Seifert longitude gives you a canonical identification between the set of slopes up to isotopy and the rational numbers union 1/0. And this identification is given by, you take the closed curve alpha, and then you send it to the fraction, the algebraic intersection number of alpha with the Seifert longitude, divided by the algebraic intersection number of alpha with the meridian of the knot. And we say that a slope is integral if the geometric intersection number between alpha and the meridian is 1. Questions about just the setup for Dehn surgery? Okay, great. So I want to introduce the main players today in terms of some different combinatorial and surgery theoretic diagrams. So the first category I'll talk about is Lin spaces. And you can just take as a definition, these are the 3 manifolds with finite cyclic fundamental group. They're the 3 manifolds that you can get by gluing 2 solid tori together along their boundary. In other words, they admit a genus 1 Heegard splitting. You can also realize these 3 manifolds as surgery on the unknot in S3. And I'll be using the convention that minus P over Q surgery is the Lin space LPQ. But this is, in general, if Q is greater than 1, this is not going to be an integral surgery on the unknot. And we'd like to have a way to describe Lin spaces in terms of integral surgeries. They won't always be integral surgeries on knots, but they'll be integral surgeries on links, which is to say that you cut out tubular neighborhoods of a bunch of knots, and then you have integer framings, you have integer surgeries on each component of this link. And so if you can write the fraction P over Q as this Herzebruck-Jung continued fraction, where each of these xi's is at least 2, and they're all integers, then you can actually realize the Lin space LPQ as surgery on this link, this linear chain of unknots, if you will, where each unknot is pairwise linked once with its neighbors along this linear chain. So those are Lin spaces. The other main player is the Poincaré homology sphere, this infamous 3-manifold that's been with low-dimensional topology from the very beginning. Here's an original Heegard diagram presenting this 3-manifold, but it also shows up in terms of surgery in some pretty interesting ways. If you perform -1 surgery on the left-handed trefoil in S3, you get this space. If you perform surgery on this link, where here each of these integers is going to specify a simple closed curve according to this canonical identification that I mentioned earlier. So if I do surgery on this link, then this gives me the Poincaré homology sphere. This surgery description is also, it also shows you that the Poincaré homology sphere is Seifert fibered, which essentially just means that it's foliated by circles. And then there are these three circles, the ones labeled -2, 3, and 5, that are somehow crushed in this foliation. And then the last interesting way that the Poincaré homology sphere shows up is as surgery on this link consisting of unknots whose linking pattern forms the E8 Dehn diagram. And all of these surgery coefficients are -2. So you can take his definition that the Poincaré homology sphere is any one of these diagrams. And so that leads us to first interesting theorem, or first interesting surgery. So if I take a look at the diagram on the left, I'm thinking about performing surgery on the black components to get the Poincaré homology sphere. And then I have this red knot F that's living inside of the Poincaré homology sphere. And if I do this surgery slope indicated by a 0, if I do surgery along the slope indicated by 0, then actually there's a very simple move in Kirby calculus, which is the calculus of manipulating surgery diagrams. If I do a slam dunk along this central 0 framed unknot, if I slam dunk the red component over this central 0 framed component, then I get this surgery diagram on the right, which is a connected sum of lens spaces. You can see the decomposing spheres sort of in this surgery diagram. And it's a connected sum of L21, L32, and L54. And so the first interesting theorem is that if I have a knot in the Poincaré homology sphere and it admits a surgery to a connected sum of 3 or more lens spaces, then actually K is this knot F. And in fact, moreover, it's this surgery. You can't get 3 or more lens space summands in any other way. It's just this surgery, which to experts is kind of the obvious one. Okay. We have some more interesting surgeries. So here we have another picture looking at the Poincaré homology sphere as a Seifert fibered space. And typically, this Greene knot is labeled by a 3. That gets me the Poincaré homology sphere. But if I instead label it by a 1, if I instead do 1 surgery on this component, then I can slam dunk this 1 framed guy over this central 0 framed guy, and I end up with a linear diagram for the lens space L76. So this is telling me that this is giving me some knot in the Poincaré homology sphere, where if I do 7/2 surgery, I get the lens space L76. The distance between, so for experts, the distance between the 1 framing and the 3 framing is 2. And I know that the numerator of this fraction's got to be 7 because I end up with 3 manifold whose first homology is Z mod 7Z. And we have another interesting surgery. This is reminiscent of the sort of the E8 Dinkin diagram presentation of the Poincaré homology sphere. So there is a sequence of Kirby moves you can do, and it's kind of the obvious follow your nose ones. If I look at this surgery diagram, C star is a knot inside of the lens space L2716. That's just according to this sequence of coefficients in the continued fraction. That gives you 27/16. If I do this 3/2 surgery on C star, though, I end up with the Poincaré homology sphere. And there's a sort of straightforward sequence of Kirby moves you can do to get there. And so the next interesting theorem is that if I have a knot in the Poincaré homology sphere and P/2 surgery on K is a lens space, then K is one of these 2 knots, E or C. And at the end, I'll talk about some interesting corollaries. some interesting open problems that this kind of wraps up. But for right now, I just want to focus on the statement of this theorem. If I have P/2 surgery on a knot giving me a lens space, then it's one of these two knots, E or C. Okay, so why should we care about the uniqueness of these surgeries? Well, it's a classical fact. For every pair of three manifolds, Y and Y prime, there's some link in Y with the surgery to Y prime. This is a result from the 60s due independently to Licorice and Wallace. It's akin to the fact that every three manifold admits Heegard splitting. So we can realize, any two three manifolds is being related by surgery on a link. But if we want to tighten the ship a little bit, we can ask, for a fixed three manifold Y, can we classify all the three manifolds we can get just by doing surgery on a knot in Y, a link with a single component? Can we reduce, what three manifolds can we get when we fix the complexity of the link inside of the manifold that we start with? And this is a realization problem. What three manifolds can I get to by surgery on a knot? And there's another question. If we're fixing a three manifold Y, are there some special knots inside of this three manifold that we can characterize by the Dehn surgeries that they admit? Are these knots special? What is special about these knots? And so these are some motivating questions that have existed in low-dimensional topology since the 60s, basically, after this classical theorem of Licorice and Wallace. And so we have some history of characterization results and realization results for knots in S3. Chiefly, we have Dehn surgery characterizations of the unknot in S3. So the unknot is just this circle that bounds a disk inside of S3. So sort of the first, major Dehn surgery characterization of the unknot is this result called property R due to Gabai. And it says that if zero surgery on a knot in S3 is S1 times S2, then K is the unknot. This is a consequence of what Gabai actually proved, which is much stronger. But for our intents and purposes, it's a Dehn surgery characterization of this knot in S3. And then a couple years later, the celebrated theorem of Gordon and Lukey in resolving the knot complement problem for S3, knots are determined by the homeomorphism type of their complements. But they did this by giving another, they showed this by giving another Dehn surgery characterization of the unknot. They showed that if non-trivial surgery on a knot is homeomorphic to S3, then K is the unknot. So we have these two characterizations of the unknot. And so like the unknot in S3, this knot F that I drew earlier, it's one of the most, trust me, it's one of the most natural knots to consider in the Poincaré homology sphere. I mentioned that the Poincaré homology sphere has this Seifert fibered structure where it's foliated by circles. This knot F is a regular fiber. And I say the regular fiber for experts because the Seifert fibering of the Poincaré homology sphere, there's one Seifert fibering up to isotopy of the Poincaré homology sphere. So F is the regular fiber. And so theorem A, in a way, gives a Dehn surgery characterization of the regular fiber. And it leads to some other conjectures about characterizing regular fibers in Seifert fibered spaces, but I won't get into that in this talk. So now I want to talk about the history of studying lens-based surgeries. And we start studying lens-based surgeries by studying knots in S3 with lens-based surgeries. So in 1971, Moser classified surgeries on torus knots in S3, torus knots being knots that live on a standardly embedded torus in the 3-sphere. And namely, showed that torus knots have surgeries to lens spaces. It's conjectured for a while that if you were a knot in S3 that had a lens space surgery, then you were a torus knot. But in the intervening years, people started piecemeal coming up with knots that were not torus knots that had lens space surgeries. And then ultimately, in around 1990, Berge devised the doubly primitive construction, which subsumed all previously known examples of knots with lens space surgeries. And this produced a conjecturally complete list of knots in S3 with integral lens space surgeries. So we have a working model for what we think are all of the knots in S3 with lens space surgeries. We just can't, we're trying to zero in on showing that these knots, the ones that Berge constructed, are the only ones with lens space surgeries. And we have partial progress in the form of the lens space realization problem for S3. So this is a theorem due to Josh Greene, 2010, in a paper called the lens space realization problem. But really, this analysis, the completion of this project is really made possible by the cyclic surgery theorem of Culler, Gordon, Lukey, and Shalin. And so this is a realization problem. We know the theorem statement is that if the lens space LPQ is realized by surgery on a knot in S3, then it's realized by surgery on a torus knot or on a knot arising from Berge's construction. And so this is the most complete information we have about lens space surgeries from S3, is that we know we can get to any lens space that we can get to by Berge knot. And so theorem B is a step in the direction of classifying lens space surgeries from the Poincaré homology sphere. It's not the first step, and it's not going to be my last step, but it is a step. And I'll now start talking about the strategy here, the framework for the lens space realization problem and for the work that I've done. But I want to pause for questions if there's anything you want hammered out. Great. So the changemaker approach starts with, if you haven't seen this before, it may be a little confusing why we would take a fundamentally three-dimensional problem and go to the fourth dimension and involve four-dimensional topology, four-dimensional smooth topology. Four-dimensional topology can get pretty hairy, but nonetheless, that's what we do. So we use four manifolds, so I'll state briefly how we use them, and we use their intersection forms. So if X is a four manifold, then the second homology of X, modulo torsion, comes equipped with a symmetric bilinear form, integer valued bilinear form. And this bilinear form is given by, if you have two classes, you can find smooth surfaces embedded in X representing these classes. And then the pairing between alpha and beta is the oriented intersection number between these surfaces representing the classes. And if X is a four manifold that you can get by attaching two handles to a link in the boundary of the four ball, which is S3. Then there's a really easy way to just read off what the bilinear pairing of this four manifold is. And it's given by the linking matrix of L. So the canonical example to have in mind for the remainder of this talk is, you remember this surgery diagram I showed earlier, surgery along linear chain of unknots. You can instead of thinking about scooping out the knots and gluing in new solid tori, you can think instead about gluing four-dimensional two handles along these knots with the specified framings. And that gives you a four manifold whose intersection form is given by the linking matrix of this link. And I'll give the intersection form of XPQ a very special name. I'll call it lambda PQ. And for me, this bilinear form is called a linear lattice because it comes from a linear chain attaching two handles along a linear chain of unknots. So this is a linear lattice LPQ. So that's one part. That's one four manifold. I want to talk about another four manifolds relevant to this setup. So I'll let K be a knot in a three manifold Y. Really think about, we assume that Y is an integer homology sphere so that things make sense, but you can really do this in any three manifold, regardless of whether K is null homologous. You just have to be careful about definitions. So let K be a knot in an integer homology sphere Y, P a positive integer, and then let's suppose that P surgery on K is LPQ. We can form what's called the trace of this surgery, which is W, and then form a related four manifold Z is below. But we'll take a look at W here. To form the trace of surgery, I take my three manifold Y. So Y here is a vertical line segment. I cross it by the interval. And then inside the one component of the boundary, I can identify a tubular neighborhood of my knot in red. And then I can just slap on a four-dimensional two handle to this knot sitting inside of the one boundary component of Y times 0, 1. And so that's how I get my four manifold W. I get my four manifold Z by reversing the orientation on W and then capping off the lens space side of this cobordism with the linear plumbing XPQ. And so if you notice here now, Z has only one boundary component, and it's Y, and it's Y with the orientation that we started with. Because we reversed the orientation on Y times 0, 1. Okay, so that's the four manifolds. This four manifold Z will plug in, we'll mess around with what this starting three manifold Y is, but this construction of taking the trace cobordism of a surgery and capping off with this linear plumbing, assuming we have a surgery to a lens space, this is the construction that's key here. And so by looking at Meyer via torus, we actually, from this construction, obtain embeddings of definite lattices, that is, these intersection forms whose bilinear pairings are definite. And so the sequence goes like this. We have lambda PQ lives in the orthogonal complement of some tau, where tau corresponds to the generator of W, generator of H2 of W. And all of this is living inside of the intersection form of Z, which we don't know what it is yet because we don't really know what Y is, but we have the sequence of embeddings of lattices. And moreover, this, this vector tau, this element tau, has self-pairing minus P. And so when we specialize to the case that Y is the Poincaré homology sphere, we have a knot in the Poincaré homology sphere, P a positive integer, P surgery on K is LPQ. We build this Z, its boundary is the Poincaré homology sphere, and the intersection form of Z is negative definite. And then we can use this theorem of Froyshov to constrain, actually try to figure out what the intersection form of Z is so that we get some concrete embeddings. And so the theorem is this: if Z is a negative definite four manifold whose boundary is the Poincaré homology sphere, then the intersection form of Z is either this diagonal form, or it's minus E8 plus a diagonal form, where the pairing on minus E8 is given by this matrix here, which, I mean, it's the same E8 as in rep theory and Dehn diagrams. It's just a happy coincidence, I think. So we start with the Poincaré homology sphere, and we know that Z has one of these two intersection forms. Sadly, or interestingly, this obstruction is actually not enough to rule out Lin space surgeries. That is to say, we can find linear lattices that embed that don't actually correspond to Lin space surgeries. But we don't want an obstruction that doesn't rule out non-examples. So what we can do is we can refine this obstruction by considering, this four manifold Z in tandem with input from Floer homology. And so what do I mean by Floer homology? It can mean a variety of things. I mean the hat version of Heegard-Floer homology. And I guess maybe I mean plus versions as well. But Heegard-Floer homology is this really powerful package of invariants of three manifolds and four manifolds and knots and links and surfaces in three and four manifolds. But basically, it associates finitely generated graded F2 vector space to a three manifolds, the Heegard-Floer homology of Y. The Heegard-Floer homology splits along spin C structures of Y. And if you're not familiar with spin C structures, these are consider Y to be a rational homology sphere, so its second cohomology group is finite. Spin C of Y is the second cohomology of Y. So a rational homology three sphere is called an L space if the rank of its Heegard-Floer homology is as small as possible, which is to say it's rank 1 in every spin C structure. And a knot in Y is called an L space knot if K admits a non-trivial surgery to another L space. And so important for us is that S3 Poincaré homology sphere and Lin spaces are all L spaces. So their Heegard-Floer homology is as simple as it can possibly be. And since it's rank 1 in all of these spin C structures, that means that essentially the Heegard-Floer homology is really contained, the information of the Heegard-Floer homology is really just contained in the gradings of these groups. And so to turn to the four-dimensional perspective, these gradings correspond to this numerical invariant called the D invariant, or the correction term. So if I have a rational homology sphere Y equipped with a spin C structure T, I can extract this numerical invariant, which is a rational number called a correction term. And these correction terms play nicely with definite four manifolds that fill Y. So definite four manifolds whose boundary is Y, Ry. So if Y is the boundary of a negative definite four manifold, then the correction term of Y in spin C structure T satisfies this inequality. I take the first Chern class of the spin C structure, thought of as a complex line bundle, pair it against itself. I add the second Betti number of X, and this is less than or equal to 4 times the D invariant of Y in T for any spin C structure on X that extends this specified spin C structure on Y. And so this inequality 1 shows up all over the place in arguments using Floer homology. But let's recall that this linear lattice lambda PQ embeds in the orthogonal complement of some vector tau inside of the intersection form of Z. But this inequality 1 actually tells us how characteristic elements of this intersection form pair against tau. And moreover, that this linear lattice lambda PQ is equal to the orthogonal complement of tau on the nose. It's not just contained in the complement. And we know this because this is just for experts, since W and this four manifold XPQ are both sharp, which is a technical Floer theoretic definition. But the important thing is that this inequality 1 really refines our lattice embedding obstruction, because it tells us some really fine information about this vector tau. And it's this consideration, combining this four manifold Z with this data from Floer homology, that gives rise to the changemaker condition that's been employed to great success by Josh Greene, Yi Ni et al., Duncan, as I mentioned earlier. So a vector, I won't belabor this too much. A vector in a diagonal lattice is a changemaker. If you take this set of pairings of elements in plus or minus 1, all of whose coordinates are plus or minus 1, pair that against your vector tau. And if that is an interval of consecutive integers, all of whom are congruent to tau paired against itself mod 2, then tau is a changemaker. This is the less, this is the less sexy, the less familiar definition, because really this admits a reformulation into this cute little combinatorial property. So if I write out all the coordinates of tau and I write them in increasing order, say they're all positive or all non-negative, then tau is a changemaker if and only if Ti is less than the sum of all previous Tj plus 1. And now this is easy to verify. This takes some work, but this is easy to verify. And this just comes out of considering Q of Z and the input from Floer homology together, is that this property of a vector is important. Where some new work starts to come in is considering the implication of the input from Floer homology. If you're instead looking at a vector in minus E8 plus something diagonal. And so I say that a vector in E8 plus Zn is a hard 8. if first and foremost, sigma is a changemaker, and this wacky set of pairings of characteristic elements of this lattice of a given norm against tau is an interval of consecutive integers congruent to the self-pairing of tau mod 2. This is in essence the same thing as a changemaker, but your ambient lattice is different. And so a lattice L is a hard 8 lattice if it can be realized as the orthogonal complement of some hard 8 vector. And so the first theorem that comes in is that if K is a knot in the Poincaré sphere, P is a positive integer, P surgery on K is LPQ, then if P is equal to 2G minus 1, then LPQ is surgery on a knot in S3, and if P is at least twice the genus of the knot, then lambda PQ is a hard 8 lattice. It embeds as the orthogonal complement to a hard 8 in some lattice of this form. Okay. So this is the obstruction that we use, that we work out to prove the two theorems I mentioned earlier. So let's revisit those. So theorem A says, F is the only knot in the Poincaré homology sphere with a surgery to 3 or more lens spaces. So we'll sketch that quickly. We know just from basic Floer theoretic reasons and lattice theoretic reasons that the surgery slope of such a knot has to be at least twice the genus of K minus 1. And we can improve this to a strict inequality, actually. P over Q has to be strictly greater than 2G minus 1 by the theory of hard 8s and changemakers. So we break it down now into two cases. If we have a non-integer surgery, which is a connected sum of lens spaces, then we can use this really nice result of Matignon and Sayari that's sort of angling towards progress on the cabling conjecture. We can use this to show that K is in fact an exceptional fiber of the Poincaré homology sphere. And on the flip side, if an integer surgery is a connected sum of strictly more than 2 lens spaces, then we can again use this cabling result of Matignon and Sayari to show that K is in fact F, this regular fiber. So we used hard 8s to get us in a situation where we could use this result of Matignon and Sayari. Oops. And then how am I on time? Oh, good. Let's go back to theorem B. So theorem B says that, oops, I didn't update this one. Theorem B says that there are only 2 knots in the Poincaré homology sphere who have a P over 2 surgery to a lens space. And so how do we get that? Well, we use the cabling construction. If P over 2 surgery on a knot is a lens space, then 2P surgery on some knot K prime is the connected sum of L21 and LPQ. And this K prime is a 2 cable of K. So we're now in the realm of we have an integer surgery to a connected sum of lens spaces, and we can use this hard 8 embedding criterion precisely because we have an integer surgery. We can't really use it yet with the non-integer surgery. So by the theorem mentioned earlier, lambda 21 plus lambda PQ now has to be a hard 8 lattice. And this is because an even number that is a surgery slope to an L space has to be greater than twice the genus minus 1. So we're in the realm of the intersection form of this big Q, of this big Z is has an E8 summand. Excuse me. And then you run the obstruction and you see what hard 8 lattices have lambda 2, 1 as an orthogonal summand. And you just see there are only two options. It's lambda 7, 6 or lambda 27, 16. This is just, you just kind of brute force, you partially brute force this. Maybe there's a more elegant way, but I'm not so elegant. I just kind of brute force this. And moreover, in both cases, so these lattice embeddings also compute the knot Floer homology, or the Alexander polynomial of these knots. And in both cases, this surgery slope P is equal to 4 times the genus of the knot minus 1. So by combining work together of Baker and Hedden and Nee and Rasmussen, you can actually conclude that this knot K, rather the surgery dual of K, is a simple knot in LPQ. That has a precise technical definition, but if you're not familiar with it, calling it simple really does suffice. And so from the fact that this knot is simple, any knot with a half integer surgery to a Lin space is simple in that Lin space. You can, I don't know, fundamental group or self-linking number, you know, any one of these simple invariants will be enough to like pick out the knots in L76 or L2716 that have Poincaré sphere surgeries, and you just find that the only ones that do are the surgery duals of C and of E. They're really the only knots with the proper self-linking numbers. And so that's the sketch of theorem B. One last note I want to point out, I mentioned earlier, this ties up some open questions. I don't know that I've ever, Steve, I don't know that I've ever seen it called this, but I decided to call it this. So if you combine theorems A and B with the finite cyclic surgery theorems of Boyer and Zhang, we obtain some nice corollaries. So the first is a classification of connected sums of Lin spaces you can get by surgery on a knot in the Poincaré sphere. So if K P over Q is a connected sum of Lin spaces, Y has at most 3 Lin space summands. And furthermore, if the surgery slope is strictly greater than twice the genus of the knot minus 1, then K is Seifert fibered, or it's a cable of a Seifert fibered knot, or it's a cable of a Seifert fibered knot. And if P over Q is equal to 2G minus, it's just equal to 2G minus 1, then Y is surgery on a knot in S3. Moreover, it's surgery on a torus knot or a cable of a torus knot. And maybe the bigger punchline here, and Steve, you really did the heavy lifting here. If K in the Poincaré homology sphere admits a non-integral Lin space surgery, then K is not hyperbolic. K, the exterior, or the complement of K does not admit a hyperbolic metric. So what happened was, due to this finite cyclic surgery theorem, the only open case, the only possible way that a hyperbolic knot could have a non-integral lens space surgery was if it had a half-integer lens space surgery. And so theorem B says that only these two knots have half-integer lens space surgeries. One of them is Seifert fibered, and one of them is a generalized once iterated torus knot, and neither of those are hyperbolic. So case closed. And that's all I have for today. Thank you very much for your time. I'd be happy to answer some questions.
Well, first, let's thank Jacob, and then open the virtual floor to questions.
Okay, well, yeah, it's really nice. Very nice stuff. So what about other types of finite? So you've done lens spaces, connected sums of lens spaces. What about other finite surgeries on knots in the Poincaré homology sphere?
That's,
yeah, I say that because people like Greene et al. Have, done a sort of thorough investigation of the analogous problem in S3.
That's definitely something. Yeah, that's something that could be investigated seriously with really, it's really promising. I think this framework is really promising for studying that. I personally haven't looked into it, but it's definitely something that seems really feasible now with this hard-8 lattice embedding obstruction. And it would follow the same, what I'm doing follows the same template that Josh laid out. That would follow the same template that Dehn et al. Laid out. But I think it's very promising to be able to, get that together.
Mm-hmm.
Sorry, could you say a little bit more about, so at some point in your sketch proof, you basically said something about upon inspection. Could you say a little bit more about what does upon inspection mean here? What are you doing?
Sure. So you break this search up into a couple of different cases. Right. So in general, this intersection form is E8 plus Zn.
Mm-hmm.
And so the three cases you break it up into are n is equal to 0,
mm-hmm.
n is equal to 1,
Mm-hmm.
and n is at least 2.
Okay.
And what happens, what you can show is that if n is at least 2,
Mm-hmm.
then this lambda 2 1 summand
Mm-hmm.
has to come from like the first changemaker basis vector you get from the changemaker tail. And so then you can classify, changemaker lattices that have that and that also embed in linear lattices.
Okay.
And then for the argument is actually pretty easy for n equals 1. You just say, the point is that the hard-8 lattice embedding obstruction, like the changemaker embedding obstruction, gives you a canonical basis for the orthogonal complement. And so you leverage that.
Okay. So you've somehow managed to push like Josh's kind of machinery into the case where you're working in E8 summand as well.
Yes.
Okay.
Yeah.
Okay. Very good.
Yeah. I maybe should have said that first, but yeah.
Okay. Because I was sort of aware of this, like the form of a hard-8 lattice sort of years ago, but I basically got stuck. I could never do anything with it because I could never understand the E8 lattice. So it was pretty cool. Is this written down yet anywhere?
It's written down, but it's not publicly available.
Okay.
It's close to being.
Okay.
It's
Well,
close to there.
okay.
Yeah.
Nice. I look forward to seeing that. Okay. And so,
I want to validate your experience. It's pretty disgusting.
Yeah. Yeah. Okay. Fair enough. I mean, I guess conceivably the cases 0 and 1 could be done by some kind of computer search.
Yeah.
But yeah, the general case looks, yeah, okay. Nice. Are there any other questions? Okay, well, let's thank Jacob again.
Thank you.